My name is Kayla Rossi. I'm an application engineer at Maplesoft, and today we will be talking about creating models of web handling systems in MapleSim and how the simulation can lead to better design of your systems. So some topics that I'm going to go over today, we'll do a quick MapleSim overview. We will then go through showing some introduction modeling and simulation and how you can build some simple models in MapleSim. With that will come overview of how to apply tension and control to your system, as well as applying a controller. We'll then look at dynamic elements such as dancers and accumulators and how we can build them in MapleSim. From there, we'll talk about addressing some webline challenges that we see, such as slippage, eccentricity, and bearing drag. We'll touch on one of these in this webinar and how we can explore paths to eliminate it. Lastly, we'll go over some converting and laminating, as well as discontinuous changes that you can model in our web handling library. And we'll conclude with questions. So first, an overview of MapleSim. It is a system-level multi-domain simulation tool. It consists of various domains that you see here on the screen. Today, we'll mostly be talking about web handling, but there are other libraries such as electrical and pneumatics and hydraulics that could also be added in combination with web handling and more. So MapleSim, as I said, is a modeling and simulation software. We do have another software called Maple that is used as a post-processing and pre-processing software in some of our apps and templates. And as well, we can extend that out to solution deployment and integration through the usage of an FMU. You can create your FMU to then talk to your PLC automation software, or use another one of our products, MapleSim Insight, to talk through Ethernet IP in the same manner. So as I said, MapleSim is a multi-domain simulation software. It is Modelica code-based and enhanced by Maple. That enhancement comes in the form of many things, largely in pre and post processing for design systems in MapleSim. And again, we have that connection for FMI, a functional mockup unit, to provide the connectivity to PLC or automation software. So the web handling library, these are a few of the components that are within our web handling library. It is ever evolving. We're constantly adding new components and new parameters to the library. But as a quick overview, we have web properties that we can add in, whether they be linear or nonlinear web properties. We have web spans, various rollers. So we have just idler rollers that can be turned into pool rollers. We have nip rollers and SRAP nip rollers, SRAP roller, and so forth. As well, these rollers can include slippage, and you could analyze your model with slippage as well. We also have sources in sync that are in the form of wind and unwind drum, as well as web source and sync. If you are looking at an isolated portion of your web line that does not involve a wind or unwind drum. We also have a sub-library for laminating, and then we have some sensors and primitives that provide some of the necessary mechanical constraints for dynamic elements in your web system, such as dancers and accumulators. So, a quick overview of building models. In MapleSim, we have block diagrams that we pull onto the screen. And so this right here is very simply stepping through a simplistic model of a rotational dancer that has a web source and sink on either side. Those are pulled onto the screen. You can change the configuration of the web on the roller with internal parameters. As well, we add in the spans between the rollers, add in some of those fixed constraints. These also house the coordinates necessary to put in the length of web between the roller points or the source and sink points. And then since we have a rotational dancer, we're adding in a revolute joint and adding some frames to these other rollers, connect it all together, and we have our rotational dancer. Of course, with signal input as well to our source and sink. And then you can get your 3D visualization of your system. One thing missing from this is plotted results. So say you were interested in tension of your web at certain points, you could always put a probe in at the location that you're interested in, and then MapleSim will also give you the data in plot form that you can export to Excel or CSV. All right, so we want to build a basic model when we're starting anew with MapleSim. And so when we want to build a basic model, we need to know some aspects so that we can start at the base level of building. So the first thing would be to bring in web properties. So this is an example of what it would look like. You would need your width of your web, thickness, density, and elastic modulus, depending on what you're interested in your web. And this is also where you would check if it's a linear web properties or not. Okay, next we would add in roller type and geometry. So whether it be a nip roller, an SRAP roller, or just an idler roller itself, this is what you would see in terms of properties. So you can put in first of all, your location in XY coordinates, as well as if it's rotated, any angle theta. But then you also have the roller diameter, if there's an inner diameter, the length of it, and then some density information as well as friction. So after we have our roller information input, then you might want to put in your speed profile for your line. So at the example at the bottom of the screen, there are some rollers that are controlled. One has speed control, which is the nip roller all the way on the right. And then we have two torque controlled rollers. One is a nip and one is just a pull roller. So we would input the speed profile or torque profile for these rollers in the form of signal input. And that is what you see there at the bottom of the screen. As well, on the bottom of the screen is an example of unwind control. There is a brake component from the 1D mechanical library that's connected to our unwind drum, and that has a signal input as well to help control the unwind speed. So as an overall summary, basically we want to know what you're interested in simulating, and that would give you the proper parameters that you would need in order to build your basic model of your system. And then from there, we can add in more complexities to match the real world system. I'm going to go through some basic building of a model. Before I do that, I just want to show you the model that I will be building. So you might have the question of how do we build and simulate web handling models? Well, like I mentioned, we have block diagrams that we use to build a schematic of the model that we're interested in. For this one, I'm going to build it live on the next screen, but it is this unwind to a rewind with a rotational dancer in the middle of it. And you can see in the block diagrams, you can see the drums, you can see the SRAP with the rotational joint constraint, as well as some control. Now, from here, we're able to obtain plotted results when we simulate it after we have all of the necessary components put in, and we can obtain not only a 3D visualization, but also the plots of variables that we're interested in. So this is a plot of all the span tensions. That's every span in this little system. You can see the tension output as well. You can see the dancer angle over time plotted there too. So now let's look at this being built in MapleSim. Okay, so this here, we're looking at a line being built rather quickly, but it's to give an overview of how you can build a line in MapleSim. So this is going through and putting in parameters for all of our components and connecting them together. The little block diagrams are dragged in from the library onto the canvas. And then we update our parameters and go through building our model. So this is going to be a model that has an SREP dancer associated with it. And you can rotate components so that it matches the configuration of your system. One thing that is being added to each component is a fixed base. These fixed base give the location or the distance between the rollers or anything with a fixed base. So that gives you your distance or length of web between two rollers. Now, this SRAP that was brought in is connected to a revolute joint because it will be a rotational dancer. So you see that revolute joint brought in, and it had some stiffness added to it as well. We can copy and paste components to quickly generate like components, which you just saw, and can add in some of the controls aspects as well. So this model will have some speed control in the form of constant torque applied to the unwind drum, and it'll have a velocity applied to the wind drum. And so for this, polynomial ramp is used for the velocity, and some probes are also being added into the system so that we can see the graphical output of what it is we're interested in, which will be the tension in that vertical span as well as the dancer angle. So it is simulated, and then we will see the results pop up. So on the left, you can see the plots of the dancer angle in degrees, as well as the tension in that vertical span. And then on the right, you can see the 3D visualization animation as well. So that was a very quick build of a model, but we will get into more detail about how to go about building some of these models. So one thing I mentioned was in regard to tension and speed control input. So you can use a speed or torque driver. These are an ideal speed control. After you build the ideal, we can go back in and add some more of your motor dynamics or add in more control and feedback loops and so forth. These control drivers are applied directly to a nip or pull roller and is input as actuation. So how do we come up with the signals for these drivers? So one way is to use a signal block, which is the example here, is a very common way. Mostly use the ramp or polynomial ramp. And this is so that there is no big spike at the beginning of your simulation due to the quick increase of acceleration. As well, the inertias of the rollers need to overcome accelerations at the beginning of your line. So by adding a ramp or polynomial ramp, it helps to reduce any of that spiking at the beginning of your simulation. You can also use a data lookup table. So these are available in MapleSim. You can input your system data if you have that from your real world system. And then you can supply it directly from your, say, Excel file to your NIP roller. So if you have your speed profile from your actual system, you can apply it directly in MapleSim through a lookup table. This is also a great way to do validation testing. If you have data from your system, you can then compare that data to the output of your simulation and see validation in that way. Lastly, if you have a very unique or complex signal input to your machine, you could always use what we call 1D motion generation app. And this creates a unique or complex signal output. We can also look at controllers for torque control. So there's two schematics here for adding torque control to your system. On the left, we have a feedback loop. So we have a speed command input as well as a PID that might house your motor dynamics, for example. And this is signal provided to a torque driver, and the torque driver is then supplying control to a nip roller. But we are also using an ideal sensor, which might be an encoder in your system, measuring the angular velocity output of your nip roller, and that gets fed back into the feedback loop with the speed command and back through the loop that I just described. You can also use a lookup table that would house your motor performance curve in it. And this is the example in the lower right-hand corner. So say you have your motor performance curve with your max torque versus speed in a lookup table. And you are sensing the speed of your nip roller. So from your sensor, it goes to your lookup table, and then that matching torque is combined with a throttle, and then that signal is fed to your torque driver, again providing the torque signal to your nip roller. Another control scheme is using a brake or clutch to regulate tension or speed. On the left is a brake component that we saw earlier. We'll see more of later on. So this brake component is connected to an unwind drum. And on the right is a clutch after a speed driver to model a torque limiter to an actuated nip roller. Both of these setups can be used to model a powder brake or powder clutch in a system or a torque limiter as well. Okay, so now we will look at adding a control loop into a web handling model. We have an SRAP dancer in the middle of this isolated web line. That's the SRAP roller you see in the center with a revolute joint attached to it. Downstream of it, we have a tension input disturbance in the form of that sine wave in conjunction with a constant tension as well. And then we will be plotting the tension of the spans downstream of the SRAP roller as well as the tension of the span that is in between the two rollers that make up the SRAP. We'll see how these tensions are affected by the disturbance, and then we will go forward and create a feedback loop taking the tension downstream of the SRAP roller and adding it to a feedback loop with a PID controller and supplying torque then to a torque control to the revolute joint in the SRAP roller, SRAP dancer. So this model is already simulated, so we'll look at the results. You can see the visualization at the bottom, but at the top we can see the three tensions all oscillating around 100 newtons at the same with the same fades. We will add in then that control loop. We have a PID controller, the tension taken from the span downstream, as well as reference tension added as to torque input to the revolute joint of that dancer. Now the controller will not turn on until 20 seconds just to show the demonstration of the tensions with the oscillation beforehand versus after the controller starts. So beforehand we see the same oscillations we did around 100 newtons. Once the controller kicks in, then you can see it compensating for that disturbance in the tensions. So if we want to build dynamic elements into our models, such as a dancer or accumulator, the dancer as an example, what we just saw in the previous slide, there are a few things that we can do to build them. First, we start with a roller, and then we need to add a frame offset for the roller. And this is found within the parameters for just a normal roller component. Then we want to add in a primitive component that would describe the motion constraint of whichever we're building. So you want a prismatic for an accumulator or a buffer, and then you want a revolute joint for a dancer. Both of these primitive components also have a bunch of parameters to describe stiffness and damping as well, and some initial conditions. So those should also have attention drawn to them when building such dynamic elements. It's important also to account for the inertia and mass of the frame for whichever element you are building. And then another thing to consider is whether you need an active actuation or if it's a passive component. And so if you need actuation, you can apply that in terms of a signal to a either torque input or a speed input using the 1D flange on the primitive joint. Let's look at a larger example of building dynamic elements using our MapleSim's web handling library. So in this example, we have an accumulator, or they're sometimes called buffers, as well as a dancer. In the center of the screen, you can see the rollers with all of the frames, as well as some rigid body frames connecting them. So this is creating that the large buffer that you will see within the 3D visualization in a moment. As well, there is a dancer on the right. The dancer is passive and the accumulator is actuated using some of the control schemes that you see at the top of the screen as well. Lastly, the two nips on either end are also controlled. So I'll start the visualization. The nips are currently stopped. They are started, and then in a few moments, the right nip will stop, at which point you'll see the dancer arm compensate for the change, and then the accumulator fills with web until that nip roller is actuated again. So another example to give for dynamic elements and having some web tension control feedback loop is this example here that is within MapleSim installations, and it is an example of web tension control with a dancer. It's a spring-loaded dancer. It has a feedback loop with an angle sensor on the revolute joint for the dancer, along with a gain and desired tension fed into a PID controller, and then that providing signal to a torque controller to control the unwind torque of the unwind drum in the system. So like I said, it is a spring-loaded dancer that regulates the unwind zone web tension. And in order to have that spring-loaded dancer, we needed to have an angle offset for the dancer to compensate for the dancer weight. And so that is calculated based on a lever arm. So a dancer arm can be thought of as a lever arm with the fulcrum at the furthest away point of the arm. So that would be where the arm is hinged. Force balance then considers the weight of the dancer roller, the weight of the dancer arm, and the force of the web tension, all derived here in this model. So let's look at some of those details now. So if we look at the revolute joint for this model, we can see that our parameters for the initial angle offset, as well as the damping and the spring constant, are input there. And then there is also a gain, and that is corresponding to the roller and the torsional stiffness of the revolute. And then this is the result that we have. So you can see the dancer compensating there for the tension at the beginning, and then it holds the tension relatively constant at 200 newtons as the unwind drum unwinds. Okay, we'll transition now into talking about some commonly seen web issues. We talk about a few of these in our web handling training itself. They're listed here. So we talk about slippage and eccentricity, as well as bearing drag. So slippage is when the web slips over the roller, or the roller slips under the web. And then eccentricity is when you have a roller that is mounted slightly off center of its axis of rotation, or you have hardware that has a parasitic eccentricity to it. And then lastly, we have bearing drag. So we know bearing drag is not negligible, but we go over how an increase in bearing drag over time can affect, how it can affect your system tensions. So for this webinar, we're going to go forward and talk about the slippage issue. Okay, so we have an example here. This example is bad for the purpose of demonstration, but bear with me. So we have 3 rollers. One is a nip roller. All of these are driven. So we have an unwind drum. I'm sorry, it's an unwind drum, not a roller. Unwind drum to a roller to a nip roller. And then you have the 2 spans that are described there. We look at our results, and we can see that the tension in span 2 is much greater than span 1. And we'd say, what is going on here? We can do a quick calculation at the boundary of this web using the friction on the roller, which is 0.2, and using the wrap angle of the web around the roller being roller 1, and that in radians is 0.4. Multiplied by the tension on the low side, so in span 1, which is about 250, we can see that we want the tension on the other side of the roller in span 2 to be roughly 270 newtons. And we see that that is not the case with span 2. It is currently about 4 times higher than what it should be. So we need to turn on the parameter of slippage for the roller. Now, turning on this parameter gives us a better insight as to what's going on. And now we get much more logical results. This is much closer to what we just calculated, of the tension in span 2 being closer to that 270 newtons. So how can we model this system without using the slippage parameter inside a roller? So how can this be eliminated? There are a few ways, and we'll go over them right now. The first way would be to change the wrap angle of the web on the roller. Next, we could also change line tension or increase the roller coefficient of friction, Or we can add a vacuum roller to the web line to, again, increase the traction of the web going over the roller. For this example, we're going to look at the first one of changing the wrap angle of the web on the roller. So one thing to note is that this might not always be possible to do in real world, but simulation gives you the ability to explore these different solutions before putting the time and man effort into changing your real world system. So here is our two configurations. Our first one, configuration 1, we have a small wrap angle on roller 1. Configuration 2, we increase that wrap angle greatly and turn off the slippage for the roller, and we can see that our tensions are now in a much more logical spot. They are different than the 270 because we have adjusted now that wrap angle, so we would get a different tension out of that calculation. So again, this is a way that you can explore some solutions to a problem that you might have. And we talk more about other solutions to other problems in our training as well. The last topic that we'll be talking about in this webinar is web converting. So MapleSim can model a few topics falling under the umbrella of web converting. So we can look at modeling laminating, which is taking multiple webs and merging them into one web. We can do converting, which is the actual converting of one web to another web utilizing conservation of mass. That's what this little example is showing on the screen, taking one web of one specific web properties and converting it to a web of another set of properties. So it might be something like calendaring, fluting, drawing, so forth. And then lastly, we can do discontinuous changes. So this has an ingoing web of specific properties and an outgoing web of another properties without the conservation of mass. So something that would be cutting or stamping as an example. So we're going to look at laminating as an example model to show using the web handling library. This is an example that is within MapleSim help, and it's a very simple laminating example. It might look a little complex, but let's go over it now. So we have multiple web properties, one for each leg of web going into our laminating web. And I can show that in the video right now. You can see there's web property 1, web property 2, web property 3, and web property 4, consisting of the order of merged web properties right there. And then you can look at each span and see which web property is assigned to which, and the laminating span being the fourth, or the merged properties, the merged web properties. So the order in which the individual web properties are entered into the merged web properties should correspond to the order of the actual web in your laminating process. So then just some overall on the model itself before we look at the simulated results. We have an unwind drum. We have 3 of them actually, and they're connected to brakes from the 1D mechanical library. These lead to a tension force on the outgoing web of the unwind drum. And then the wind drum, which is winding up the laminated material, is driven by a torque source, also from the 1D mechanical library. This allows for pre-tensioning of the web line within the first second of simulation based on the control input. So if we look at the results from this model, we'll look at the strains in the web as well as, in the webs coming into lamination, as well as the outgoing tension and web speed. we can see from the plot at the top of the strains that the curve of the strain of the ingoing web lines at the laminating point, there are some oscillations during the startup phase, but after the startup of 5 seconds, the web line obtains a constant speed. The strain then increases slightly over time as the radius of the unwind drum components decrease. On the other side where the wind drum is, those are the plots at the bottom. The tension in the span decreases after the startup phase. This decrease is due to the constant torque that is in the wind drum and the increasing radius of the wind drum. Okay, a more complex and larger laminating system might look something like this. This is what the block diagram that you build in MapleSim would look like. So at the top we have four different web properties. The first three correspond to the unwind drum web properties. So it'd be the orange, green, and blue. And then the fourth is a merged web. You can tell by the difference in icons. So that would be the web properties of the dark gray web that's being wound on a wind drum. Now in the block diagram, you see corresponding blocks or squares to the colors of the web lines above, and these represent subsystems that you can create when building models in MapleSim. You can see that, you can see from the 3D visualization that it's 3 unwind drums that are coming together to create the laminated web. And from the block diagram on the bottom, you can see all the 3 different breaks that are then controlling the unwind drums. To get a closer look at these subsystems, so the first orange one, you can see all the rollers and webs in that line, as well as the unwind drum, and I can go through the others in the same fashion, and it just shows you how you can create a more compact and neat example, neat model in MapleSim. And that is all that I plan to discuss today. If you are interested in our web handling library, I encourage you to reach out to us at the information on the screen right now. Thank you for your time today, and I'm happy to take questions as well. There is a URL on the screen that can give you some more information about MapleSim. Thank you.